Okay, guys, let's start. What do you think? Is this aircraft landing or taking off? I just have to move.
Landing.
Why?
It's flaps.
Okay, but flaps can be down on takeoff as well.
It's taking off because the wheels are already half back.
Yeah, it's very hard to tell from this image. Probably it's landing, but because there is a gap between the wings and the flap, and it happens when the flaps are very highly set. So this is an Boeing 737-800 landing, probably. This is 787 trying to stop on the runway. You can see the flaps are down and air brakes, speed brakes are deployed, and thrust reversers as well. The thrust reversers just push the air in the direction of movement of the aircraft. And what's this?
Not good.
Not so good. This is Turkish Airlines flight 1951, 25th of February 2009. There was a faulty radio altimeter on board, and the crew didn't take a good reaction. So in fact, they just crashed 1.5 kilometers just before, in front of the runway. It was the approach to Schiphol Airport. What we are going to talk today is how we can prevent these kinds of things. You can't prevent these things of happening because it's due to pilot error or faulty radio altimeters or different instruments, but you can do something else. You can see the black box. You see this is orange. Usually people think that it's black, but it's in fact orange because you want to easily spot it in nature, because nature is usually blue and green, so not so many orange things in nature. It's red-orange. And this is real image of a black box. So my colleague and myself, Raf and me, we're going to try to tell you how we do this, how we try to prevent these things of happening. And we are going to do whatever we can to do that. So first I'll tell you something about what the flight data monitoring is. Then I'll teach you how to become a flight data analyst in 1 minute. Okay, that's it. You'll see some real data coming from black box. And we'll talk just a bit about engine health monitoring, and we'll pose the problem, and hopefully we'll bring Raf on the stage and he'll solve the problem. We're not sure, but we'll try to do that, okay? It's very hard to condense everything in aviation just in one presentation. So flight data monitoring is just what the title is saying to you. You have to monitor your flights. Why? You want to find the deviations from the safety operation. So the idea is to make flying safer. It should be non-punitive, because you can have a sensation of big brother sensation, because the pilots have to give away their data. In fact, they don't do that voluntarily. It's a mandatory thing. So you're looking at how they fly the planes. So imagine one looking at your data coming from your car, and you just say, okay, you are sacked because you just had you speeded up on the motorway. So you shouldn't be punitive, and you will run out of pilots very soon if you do that. And the data is very confidential, quite sensitive data. And the problem is that sometimes it belongs to pilots, sometimes it belongs to airlines, but you don't want to disclose any kind of such data. It's very confidential. You can do that just in case of accidents, serious accidents. So this is Airbus 320. Sketch of Airbus, and there's an important unit mounted on it, and it's called Flight Data Acquisition Unit. And this is the place where all the sensors wiring is coming. And from this unit, by using wires, the data is stored in the aircraft black box. What do you think where the airbox is on this aircraft? Yeah, who said that? Okay, thank you. So the flight data recorder can be anywhere. It's usually in the tail section of the plane. But now the problem is we would like to analyze that data and to find insights from the data and see, okay, these pilots are not doing these things properly. Not the pilots. We don't want to blame the pilots. It's our operation, how we set it, okay? But the problem with this is that it will be very expensive to you just take the black box off the aircraft and to get the data out and put it back. So you don't want to ground the aircraft. We all live in the world of very tight profit margins in airlines, so you don't want a grounded aircraft for that. So we have something else. This is quick access recorder. It's a small device mounted behind the crew in the cockpit, and it just uses the camera card to collect the data. It's completely the same data that's coming to data acquisition unit. It just splits into two bits and pieces. The idea is that you can easily just take out the card and upload it to a server, and we can analyze that data.
Sorry, could you explain again?
Yeah?
What's the difference in the data between the data acquisition unit and flight data recorder?
Data acquisition unit is just an electronic box that collects the signals.
Isn't that what the flight data recorder does?
You have to collect the signals in one place, then you will distribute this by wires to flight data recorder. You have to have a thing that first, you can't feed the flight data recorder with all the wires, 5,000 parameters or 2,000 parameters, sorry. So first you have to condense these 2,000 parameters and then just use one wire to put it into flight data recorder, okay? So how we do this? First you have to have an aircraft flying, taking off, flying and landing. And the data is copied to servers. It can be done automatically, wirelessly. Some airlines do that, but you can also, as I told you, you can just take out the card and just upload the data on the servers. Then data cleansing. Oh, there is NumPy master race. There's some Python. So yeah, okay. And sorry, but this is a very, very time-consuming process, because, and you know that you're the data people, so it can take very, very much time. And then the data is being analyzed by the software. It's in-house software. And then we detect the events on the aircraft. So one of the events can be hard landing. So the crew just smashed into the ground, and there was a value of 2.0 G, and passengers were not so, they were reluctant to say that it was a smooth landing. Yeah. So, yeah. So we do these kinds of things. So, but yeah, this is just to break the presentation into two parts. But since you've already had lunch, I put this one. But by no chance, this is, I don't try to advertise Java here. You see but everything is written in Python, okay? Now, I promised you that I'm going to try to make a data analyst, flight data analyst of you in just 1 minute. So what I'm showing you at the moment is the flight profile. This is the altitude profile. And you can see that at 3:51, the aircraft was on the ground, and it goes up, cruise, and landing, okay? Now, we see that there is an event here around 5:15, and I'm going to enlarge the axis. I'm going to zoom in that data. So the shaded area is this area. And I'm going to give you two parameters, airspeed and altitude. And I'm going to give you engine power. Just disregard N1. The red line is one engine, the green line is the other engine. What do you think happened here? I'll give you 30 seconds to 45 seconds time.
Wow.
What?
The tower said abort. There's probably too many stacked in the queue. 'Cause I've been on a plane that's done that.
But what was the minimum value of altitude? No, it's about 300 feet. Sorry for the scale. Yes, it went go around. It was too low altitude to say that they were re-queued. You don't do that at such low altitudes. The lower to the ground you are, the riskier the operation is. So you don't do these kinds of things. It was a go around. So what crew did, it just pushed the throttles up and accelerated. And there is another parameter, pitch. So this is the angle with respect to horizontal surface. So they're pitching up, adding full power above 100, and the aircraft goes up. And you can see these smooth lines. So it's not instantaneous. The engines need some time to react to your commands. In the table, this is the data. You will see that pitch is 15.1. So it's marked as a red event because you're not pitching in 15 degrees when you land. You usually want to go steadily down. And the other thing, the engine power was above 100%. Percent is just a nominal value. It can be, above 100%, but it's, So it's very much power put into the system. So this is N2 exceedance, or just power exceedance, and this was marked as a go-round event. And in fact, it was a go-round event. We don't know from this data why. Was it due to bad weather or something else? this is, what was this? Hopefully it's not an engine of an aircraft. Yeah, but this is an old agricultural steam engine. But for those of you who like jet engines, there's a schema. And since we all hear from data land, we can abstract those things. You don't have to know aerospace dynamics of things, blah, 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 to understand this. So the interesting bit is just look at the colors. There is a green color shaft, and it's called low pressure shaft. And it's characterized by one number, rotation speed. Okay? We are abstracting the parameters. And there's another one, N2, the purple one. This is the high pressure shaft. And you have to put some, so you are producing pressure in the engine, and then you have to put some fuel. And this fuel burns, and you have exhaust gas temperature. To simplify things, I'm just going to disregard these first two parameters because we are going to play with the model with just fuel flow and exhaust engine temperature, exhaust gas temperature. So these two are in play. If you have 4 engines, or 2 engines, yeah, usually you have 2. But if you have 4 engines, then you can keep pairs of parameters together. So now you have 8 parameters. You don't have just 2 parameters. So this redundancy will help you to lower the variance in the result. What happens at takeoff? Fuel flow is about 500 liters per kilograms per hour, and it's steady there. So probably aircraft is on the ground. You see pitch is 0, so the slope is 0, just sitting. At a certain point, it will get the takeoff clearance from the ATC. And then, when they get the takeoff clearance, they will put some power to the engines. And you'll see there's some time needed for this to go up. So fuel flow starts here and goes up while they're accelerating down the runway. So you get the maximum fuel flow, but they're still on the ground. You said the pitch is 0. After that, a takeoff happens, approximately here. Because pitch is going up, they're pitching, they're rotating. Aircraft pitches the nose and goes up. The interesting bit here, after 20 seconds into the flight, the crew presses the VNAV button. So this is vertical navigation. Yes, some people think, okay, who is flying the plane? Usually, they will just press the button, and the computer will try to adjust. So they're taking off because it's very risky to be lower to the ground, and we still believe humans are better. Some people will not agree on that. But what his pilot pitches the aircraft, but at a certain point he says, okay, computer, take over. And the computer takes over. What happens as a result of that, the computer thinks that it has to maintain lower or higher speed, and it will adjust the fuel flow to have an optimal performance takeoff, or whatever that means. So in a few seconds' time, in fact, you will see this drop in fuel flow because the computer will try to accommodate for the new situation. And it happens just a few seconds after the autopilot was engaged. And we want to detect this point. Okay? And it's a big problem. If this point is not detected properly, we'll have a problem with the engine health. Because during takeoff, higher values of power are allowed. You are not allowed to have 100% power in cruise. Okay? So if you just disregard this point, then you might miss the opportunity to see that something is wrong, how the engines are handled. So the pilots are using too much fuel, too much power, and they will have to go to maintenance too early. And this is losing money, in fact, and compromising flight safety. So it's extremely difficult. We try to do that deterministically, so with classical signal processing. So differentiation of signal. The signals are very much different, and they vary across very different aircraft families. The third problem was, what if a parameter fails? You have 8 parameters recorded on a Hercules aircraft and 105,000 approximately on 1,500 parameters on Airbus 380. And then you just can't, the parameters will fail, but it's not that the aircraft can't fly, okay? So it happens all the time. So we have problems with missing data. We have to handle it very frequently. And this kind of, you have to retrain the model, make a different model, another dependency tree if your parameter fails, if you don't use statistical approach for that. So the solution is just to use the VNAV when the autopilot was engaged, and try to find the drop or raise in fuel flow and exhaust gas temperature, and we'll try to find the changes around those times to mark the point correctly. We'll gather the knowledge and try to calculate the probability for the end of takeoff for an unseen flight. So these three parameters are in the game. And now Raf will continue with math. He asked me before this presentation, I'll just tell to people that we are going to do some Python. So I just forgot, so you'll have to. Yeah. Sorry for taking up too much time. Just use it.
Okay, so as Marko introduced, I will be talking about the detection of the end of takeoff point. How we're gonna do this? It's we will be using probably a probabilistic approach, and we will have a model that is divided essentially into parts. First part is we're going to have a probabilistic approach, and in the second part we're going to have a data-driven approach. Essentially, we want to collect probability distribution from a number of flights and then apply all the probabilities that we have collected to predict the end of takeoff point for a new testing flight. What's the main tool going to be? It's going to be, of course, Python, and okay, it's going to be Python with the standard classical libraries, NumPy, SciPy, scikit-learn, and we're going to use PyMC. So if you have followed any course, any tutorials, or any other conferences, any other talks, you know a bit of PyMC. I will give a very short presentation of that. But first of all, let's talk about the data. As Marko said, we have the data in our server that is stored as an HDF file, and in order to load the data and explore the data, we use our flight data accessor, that is an open source tool, and it's well documented. It's on GitHub. This is the screenshot of the documentation page. As you see, one main point is about the masked arrays, and that's it's a very important tool that we have, because masked arrays are telling us if a certain parameter is failing and how many times this parameter is failing. As an example of how to use our HDF access, there are many ways. You can subclass our HDF file. You can use the with key that is very Pythonic, and you essentially access the data as a normal Python dictionary. Now, all the data, each parameter is recorded at a different frequency. For example, the normal G is recorded 8 samples per second, whereas the pitch is recorded a sample per second. Therefore, we have, first of all, to align each of them, and in this example, we align each of them at frequency 1, and this is an example of showing the pitch and E1N1, that is the power of the first engine. And as you see, before the second 500, there is a piece of missing data. That happens not so rarely, and when that happens, we really don't want to use that data in order to fit our probabilistic model. What's the strategy? We have as I said before, we have a two-step model. First of all, we create our probabilistic model, we fit the model. So we collect the parameters that we want, we detect the vertical navigation engaged, and we just look for a window around the vertical navigation engaged, because we know that at the end of takeoff it will happen around that point. We run our model and we collect samples for each flight, and then we will collect all the samples and we will use those samples to predict the end of probability for different flights. Why do we have a different two-step model? Because not all the flights have the vertical navigation and because sometimes the vertical navigation may just fail as parameter. What happens there? This is not going to scroll down, right?
Can you just
Okay.
hold it?
No, it doesn't work. You go to the, you just come out and look at the notebook raw, because I tried that on my slides.
Yeah, no, I went through the JavaScript, the reveal.js yesterday night, but we had to swap this, so I probably made this is the old reveal JavaScript. Okay, that's fine. So here I'm just going to present a very simple model. We are going to use just two parameters, the fuel flow and the exhaust gas temperature for only one engine. And essentially what happens is that around the vertical navigation, those two parameters are piecewise constant. There will be a drop at some point, and that drop will be precisely the end of takeoff. So we want to understand when that happens. The data, those parameters are time series, and we want to find the distribution probability that each point is the end of takeoff point. The key tool will be PyMC, that essentially is a very powerful utility to run Markov chain Monte Carlo methods to sample from a statistical model. Well, also the LaTeX does not work, that's good. Okay, so since I don't have this, I can just show. Oh no, it's loading. Okay, so hopefully it will be loading at that point. We apply Bayes' theorem to compute the posterior probability of our parameter given the data. Now, I don't have the formula here, but if you just have in mind that we have a certain probability of a number of parameters given the data, by Bayes' theorem, that is equal to Can I just swap this?
For your info, I erased the formulas so you don't bother the people.
I know, that was just too much. Yes, exactly. This is kind of a probabilistic programming approach. You never know if something works or not.
Oh, way back.
Hey.
And yeah, I can also scroll. That's amazing. Okay, so no prediction is already too much. Okay, so we have our list of parameters. That is the time point, the fuel flow. Here we have fuel flow 1 and fuel flow 2, which means the mean of the fuel flow before and after the end of takeoff. And EGT1 and EGT2, it's the same, the mean of the EGT before and after. Bayes' theorem is telling us that the posterior probability, it's essentially the product of the likelihood, that is the probability of the data given our parameters, times the priors, the probability of each parameter. Now, we model this in this way. We have the likelihood, here I'm just considering two parameters, FF1 and FF2, and the likelihood will be a normal distribution that where the mean is the FF before the end of takeoff and after the end of takeoff. For the priors, we have the timestamp, the time point when it happens. We don't know when it happens. For us, it can happen anytime between second 1 and second 20. Remember that we have a 20 seconds window around the vertical navigation. And the mean of the full flow before and after, again, this is a signal, we have certain noise, so we give as prior distribution a normal distribution with mu equal the mean of, depending on the data, the mean of the full flow that we are feeding, the data that we are feeding the model with. When we take the EGT into play, we will change our likelihood to be a product of one-dimensional normal distribution. We consider the parameter to happen to be independent to each other, and this essentially it can be easily increased to multiple dimensions. We can have this for one engine, for two engines. We will have a similar likelihood and similar priors. This is an example of how things work in PyMC. I'm not going to go through this code line by line. This is just to say that that's the class where I define my priors probability and the likelihood. Essentially, as you see, for example, EDX represented the time, and it's a discrete uniform probability between 1 and here length of the data, which will be 20 seconds. I can probably stress on how you run the model, how you run the sampling. This is PyMC2, so here what I do is creating a class and creating my data model just to be all the variables that are defined in this class. In PyMC, you create a model object, and then after that an MCMC object from where you sample. In this case, we sample for 10,000 times. The second number, 8,000, is the burn-in period. Essentially, at the end of the sampling, we will have 10,000 samples for each parameters, and we discard the first 8,000. And the 2 is the thinning, which means essentially it serves to decrease the autocorrelation. The idea of the Markov chain, the MCMC, it's an acronym for Markov chain Monte Carlo, is essentially doing a random walk in a multidimensional space. Nothing is really random, therefore there can be autocorrelation, and we want to decrease as much as possible that. Therefore, we run our model. This run and plot is essentially a wrapping function where I load the data, I clean the data in the sense that I detect the vertical navigation and just take the parameters around those 20 seconds data points. I run my two-dimensional model with the full flow and EGT, and what I have is this bunch of histogram. Each histogram is representing the samples that I collect after the MCMC run. So as you see, there is a very clear difference between the full flow before and after, as well as the EGT. In this case, sometimes it happens, you have that the possible probability is just fixed at 16 seconds. All the samples are converging around that number. And this is because in this case what we have is that when we look at the full flow, that's the blue line, there is a very steep decrease of this parameter as well for DGT. Here the scale, I apologize for that, it does not give the best idea, but there is a huge difference between the before and after. But the other question is, what happens if one parameter fails? We have a masked array, we can give a threshold. If more than 5% of this data is masked, then we don't want to use that parameter. That will be contaminating our model. In this case, we can just run again our model. In this case, in one dimension, we will just be considering the full flow. If, for example, DGT fails, and this essentially again the trace is plotted as histogram, and this is the same data as before, so it's not a surprise that again it's 16 seconds. Now, the second part of the model, it's about prediction. We have a new flight and we don't care if there is the vertical navigation parameter or not. We just want to look at the first 5 minutes from the takeoff to seconds 500, because we know that the end of takeoff must happen in the first 5 minutes. So what we do is running the MCMC in a number of flights, 200 in this instance, and we collect all those samples in order to use them for the prediction part. Now, I've run my model for 200 flights, and this is the distribution of the fuel flow before and after, as well as DGT before and after. And in the third line, EDX apps, so the first graph here, the first histogram, it's representing the end of takeoff, the distribution of the end of takeoff from the takeoff point, so 30 seconds after the takeoff. So what's the strategy? How do we use these samples? Well, again, we apply Bayes' theorem. So Bayes' theorem is telling us that if I want to check if a data point is what's the probability that a data point is the end of takeoff, I just have to compute this product. So the likelihood would be the end of takeoff given my parameters, and the prior will be given by our prior knowledge on the parameter that will be the time, the fuel flow, and DGT. And precisely the likelihood will be used, will be inferred from our histogram. Not yet. So in this example, we have no, we don't really know when the end of takeoff is happening. We know that for sure it cannot happen in the first 15 seconds. It's just too early. So for the time, we have a discrete uniform distribution between 15 seconds and 300. And for the fuel flow and DGT, again, we give a normal prior distribution. For the likelihood, we will use the data. In this case, I'm just showing how to have a probability density function from our histogram. In this case, we use SciPy stats, the Gaussian kernel density estimation. Here we can use scikit-learn, or again we can use another run of the MCMC again. But for production purposes, this is the fastest. One. And this is an example of what happened for a given flight. Here, the real end of takeoff is at 41 seconds, and essentially we computed this probability at each point in time from the takeoff up to 5 minutes. And we see that the prediction is around 42 seconds, which essentially we can use also this data to assess our previous model. We can run this prediction algorithm on all the data, on all the flights that we used to fit the model. And we can have some metrics to assess that model. I'm not showing that here for, because of the time, I guess I'm already overgoing, so if you have any questions. Probably say that there's also a software developer, probably also a data science, if I don't know how I've done now. And yes, for the PyMC reference, there is it's really good that the actual documentation of PyMC, and I strongly advise you the Bayesian methods for Hacker by Cameron Davis Pillow, that is actually also open source on the notebook behavior of in Jupyter.
Yeah.
You were talking about detecting end of takeoff. Do you calculate other features as well? For example, determining incorrectly trimmed or incorrectly weighted flights. You have to increase the engine velocity higher than you're expected because you're not taking enough of the crew.
You have, I don't know if you need this for the camera. Just put it. You, depending on what you're trying to achieve, you can do that. And there's a thing called derated takeoff, where in fact the crew doesn't set, you can't see this. You can't see the drop in fuel flow going up. It's just a straight line. Why they use it? There are reasons for that. But the idea is to make a long story short, is that we will not in that case be able probably to detect this point because we will be fitting the noise. But we can always snap to the old traditional hard threshold of 300 seconds and say, if you reach 300 seconds and we weren't able to detect that point, we'll say 300 seconds is a limit. And we have another limit, it's 3,500 feet. So if you reach 350 feet, you should have gone over the VNAV or over the end of tables. Hopefully, does that answer your question? But very good point. Yes, there are many parameters that depend on that. Yeah, it's not about the Malaysian flight. No.
Does the temporary recorder also contain the flight voice recorder as well as the flight data recorder?
That's a very good question. I know some people who try to do something with the cockpit voice recorder, but still this data is not being analyzed.
Okay.
Since we don't use it. Yes.
Is there public anonymized data sets we can look at?
I'll probably provide only a couple of files. The problem is that it's very hard to identify these flights. So and the key problem is that this is very confidential.
We usually don't. Sometimes we can, but sometimes the identification is harder than you think. Because you can know by knowing along the lot, you know from which airport it took off.
Yes.
And if you know the airline, if you have just one airline flying to that airport, to Greenland somewhere, you know who's flown that flight. And sometimes it's very hard to do that.
So you said they release it sometimes in case of accident. Are those?
Just in case of the accidents and for regular maintenance, then you take off the black box from the aircraft.
But are those HDFs available for download or?
No. Should be a good thing. We are also doing some data sharing programs where airlines will share their data. We don't have, unfortunately, time to talk about that, but these are very interesting concepts. When, for the sake of flight safety, airlines can group together and share their data. So the pilots have the prior knowledge of how to fly the plane, but if he gets into an unknown airport, he will be able to know the issues in that airport. So he will be able to respond to the requirements of landing, because it's easy to say land an aircraft. It's not so easy when it's dark outside and you have strong winds blowing from one side. It's challenging.
Is the VNAV button you're pressing not recorded at all?
Yes, it is.
It is?
Yes.
Right, and you use that to train on, do you? Or?
Yes, we use the VNAV for referencing the point.
Right.
So we start from there to find the drop in fuel flow that we detect as the end of
Do you actually know when it's been pressed?
Yes, this is just a binary variable, 0 or 1.
So why?
We have many more categorical variables than than we have continuous analog variables.
So why do you not just use the VNAV?
Because sometimes the VNAV is corrupted. That signal may be corrupted. Sometimes it does not exist at all. Not all the aircraft may have the VNAV button or may record that signal.
Or the parameter can be broken. Yeah.
Sorry. Why is this data so confidential? It seems like there are websites where you can go and track planes taking off and landing in real time. Why would things like fuel flow be super confidential?
No, it's not just the fuel flow, it's the data. In Europe, you have how many countries? And every single country has a body that regulates the safety. So you have civil aviation authorities that regulate how the data and whose data is. In fact, the data, Chris, can you help me? Who has in Germany, I think the pilots own the data, and probably for the rest of the Europe. Yeah.
If you take fuel flow as an example, so then it's a commercial problem. So you've got one operator that flies with higher fuel flow than another, and suddenly that operator is able to compare his operation to another operator and say, well, we can do this cheaper, or we can do this more efficiently, and so on. Then it becomes like a commercial.
That seems like it might be it seems like this would be a public value.
Yeah.
Is it just like commercial
No. We are open source completely with respect to safety. Sorry, with respect to safety things. We are completely open source. You can download our algorithms that we use in production. But the data, we don't own the data. We owe the parameters and calculations that we gather from the data. So it's readily available, but all the technologies that we use are open source. Postgres, SQL, Python, I don't know, R, all these kinds of things. But the data is not ours.
One issue is probably you mentioned that you don't want to be blaming pilots.
Yes.
So if you open up the data whilst the pilots may trust you not to blame them, if they open up the data to the rest of the world, they may be more open to criticism.
How would we know who those pilots were?
That's
not like another way.
This is, yeah, but you...
I appreciate it.
Yeah, but you just nobody will try to fly an aircraft. I mean, you will not have any pilots. Because they already know that they are being monitored. Because the legal requirement is that they are running the FDM program. So now when you start, sharing the data across the globe for the good of everyone, it's not an easy process. And they're very traditional in aviation. That's why they have checklists, and the safety is really... But your point is great. I mean, yeah, we would like to do that, but the only way we can do is through data sharing programs where they do that voluntarily. I mean, they're not pressing to those.
Are there any airlines that open up their data?
No, not that I know.
Okay.
Yeah?
Thank you.
Yeah, it might be. More questions? We can discuss a break if you like. Thank you very much for coming, guys.